Welcome to aminacademy.com. In strength of materials, let us discuss about laminated or leaf springs. Laminated springs, which consist of a number of parallel strips of a metal having different lengths and seam width, placed one over the other. Initially, all the plates are bent to the same radius and are free to slide one over the other. It shows initial position of the spring which is having some central deflection delta. The spring rests on the axis of the vehicle and its top plate is pinned at the ends of the chassis of the vehicle. When the spring is loaded to the design load W, all the plates becomes flat and central deflection delta disappears. Now look at here. The overall purpose of leaf spring is to provide a support for a vehicle. It also creates a smooth rider, absorbing any bumps or potholes in the road. Additionally, the leaf springs are used to locate the axle, control the height at which the vehicle rides and keep the tires aligned on the road. Because of their benefits, leaf springs are in high demand. Casual transportation is just one way leaf springs have contributed to our transportation industry. These days, leaf springs are more popular with heavy commercial vehicles like trucks and SUVs and vans. The parts of the leaf spring follow are some main parts of the leaf spring: metal plate or leaves, master leaf, central bolt, U-bolt, rebound clips, spring eye, shackle, rubber bush. These are the structural of structural figure of leaf springs. Here, look at this. These are master leaf. This center clamp is clamp all leaves together, and graduated leaves. Then next leaves are reduced length and span to L. This is a rebound clips. Metal plates or leaves. Leaf springs consist of several metal plates or also known as leaflets, layered on each other in decreasing order of their sizes. The leaves are given a curvature called camber, which gives the leaf spring a semi-elliptic look. Master leaf. The longest leaf at the top of the spring is known as the master leaf. It is curved at both ends to form a spring eye. Two bolts are inserted through these eyes to set the leaf springs to the automobile body. Now we'll discuss further about structural design of leaf spring. Here let B equal to width of the each plate. B equal width of each plate. All widths are same. N equal number of plates. And L equal to span of spring. Sigma equal maximum bending stress. Maximum bending stress developed in the plate. T equal thickness of the each plate. W equal to the point load. W equal to point load acting at center. Acting at the center of the spring, and delta is original deflection. Original deflection of the top spring here delta. Now we will get expression for maximum bending stress. Or maximum bending stress. Here the load W acting at the center of the lowermost plate will be shared equally on the two ends of the top plates. Therefore, bending moment Bm, that is bending moment at the center, is load at one end into L by 2, half of the length. Therefore, bending moment M is W by 2 into L by 2 is WL by 4. The moment of inertia Mi, inertia of each plate, Mi of each plate, that is I equal BT cube by 12 because it is a rectangular plate. But the relation among bending stress, bending moment and moment of inertia I is, the relation of these things is M bending moment, Y moment of inertia I is equal shear stress over Y. Therefore, M equal shear stress over Y into I, which is equal, shear stress is sigma and moment of inertia is BT cube by 12 over Y equal thickness by 2. Now, which is equal, by simplification, it gives sigma BT cube over 6. Now, total resisting moment. Total resisting moment is number of spring into bending moment M, which is equal N into sigma BT cube by 6. As the bending moment due to the load is equal to the total resisting moment. Therefore, here bending moment is equal to total resisting moment. Therefore, equating both, that is here, it is 2. Therefore, equal that to WL by 4. WL by 4. This, let it be 1. WL by 4 is equal to total resisting moment N sigma BT cube over 6. Therefore, we have the relation sigma shear stress equal 6WL over 4 NBT cube equal 8. Your 6 by, what is 2 by 3 comes 3WL 3WL by 2NBT 2N BT, no, BT square here, mistake here, BT square. Two N BT square. Therefore, sigma I can write clearly here 3WL over 2N BT square. Now, consider expression for central deflection. Central deflection delta. Here, look at this figure. Now, this is L by 2. This delta here, you know that here radius R minus delta. The total radius is R. Point A, B. Here, R is the radius of the plate to which they are bent. Here, from the triangle OAC, this point C here, triangle OAC, AO square, that is AO square is the hypotenuse, that is AC square plus CO square. That is your R square is equal, AC square is L by 2 the square, then plus OC is, CO is R minus delta the square. That expression here R squared equal to L squared by 4 plus expansion of R minus delta square is R squared minus R delta plus 2R delta plus delta square. Here delta square is neglecting, delta square is neglected because it's a smaller compared to other. Neglecting, we get R square equal L squared by 4 plus R square minus 2R delta, and this both R squared cut. From this 2R delta equal L power L squared by 4. Therefore, delta equal L squared by 4 into 2R. Therefore, we can say deflection delta equal L squared by 8R. This is a relation for deflection. But the relation between bending stress, modulus of elasticity, and radius of the curvature is given. We know that relation sigma over y is equal Young's modulus over R. From this, R equal Ey over sigma, that is equal Et over 2 sigma. Since y equal to T by 2, half of the thickness is equal y. Therefore, we can write the complete relation like from this delta equal L squared into 2 sigma over 8 Et. Therefore, delta equal to 8 cut as 4, that is sigma L square over 4 Et. This is a relation for deflection. So far we discussed about the construction of leaf spring and expression for sigma and delta, that is shear stress as well as deflection for leaf spring. If you have done, please subscribe our YouTube channel.